Greetings, dear participants. Let me introduce my study, Routing Attack Detection in IoT Networks using LSTM Autoencoder. The progress of the Internet of Things is impossible without protocols optimized for weak devices, such as 6-low WPAN or RPL, which allow them to connect to the Internet via IP addressing. These protocols are vulnerable to various attacks, including routing attacks, which can disrupt communication, disrupt data availability, and compromise data confidentiality. Routing methods, depending on the network architecture, are classified into location-based protocols, linear algorithms, and hierarchical algorithms. Traditional routing methods don't consider network overload caused by low bandwidth, long processing delays, packet loss, and resource exhaustion. This overload reduces service quality, lowering network performance and reliability. Therefore, ensuring full security of IoT networks requires not only developing new protocols and routing methods but also integrating attack detection mechanisms. Approaches to protecting against such attacks include routing information authentication mechanisms, route filtering, monitoring for abnormal activity, cryptographic traffic protection, and implementing trust models in wireless and mobile networks. The limitations of current protection methods are presented on slide 3. The authors proposed a method based on LSTM architecture capable of preserving long-term dependencies in time series, which is important for analyzing network node behavior patterns. In the context of building routing attack detection models in IoT networks, the selection of input parameters is crucial for accurately representing both normal and abnormal network node behavior. In this study, 5 key features are used. You can see them on this slide. These features were chosen due to their ability to reflect critical aspects of the RPL protocol's operation, as well as their sensitivity to anomalous influences caused by external or internal threats. Authors implemented an architecture for anomaly detecting in time series of routed IoT data based on an LSTM autoencoder. The model combines deep learning with preprocessing of data and statistical evaluation of deviations. The architecture is based on an LSTM layer with 64 neurons and a ReLU activation function, which allows the model to take into account dependencies in the time dimension. At the encoder stage, the input sequence of size 10 by 5, 10 time steps with 5 features, delay, ETS, battery, hop_count, parent_ID, is compressed into a latent vector of fixed length. The model is compiled with the ADAM optimizer and a loss function in the form of mean square error. Training is performed on normal samples selected from 80% of the sample, with subsequent division into training and validation subsets. The number of training epochs was 50, and the batch size was 32. Min-max scaler was used to normalize the features, which guarantees scaling of values within 0, 1, which is important for the stable operation of LSTM layers. After training was completed, the model was applied to the test sample to reconstruct the sequences. The error rate of each sample was calculated as the average square difference between the initial and reconstructed data across all features and time steps. To separate normal and abnormal examples, an error threshold was determined based on the 95th percentile of MSE values on the training set. All samples that showed a reconstruction error higher than this threshold were classified as anomalies. The CIC-IoT 2023 dataset was used to generate the data for this anomaly detection task. During the experimental study, a system for detecting routing anomalies in IoT networks was modeled based on an LSTM autoencoder, which was trained exclusively on normalized, safe data. The total size of the initial sample was 10,000 records, evenly distributed between the safe and unsafe classes, 5,000 each. To train the model, 80% of the sample, 8,000 records, was selected, including 4,000 normal and 4,000 abnormal samples, but the training process itself was performed only on normal samples. The remaining 2,000 records, 1,000 for each class, were used to evaluate the quality of classification during the testing phase. The LSTM autoencoder model was trained for 50 epochs using the ADAM optimizer and a loss function in the form of mean squared error, MSE. Analysis of the confusion matrix for the test set showed high classification accuracy. The model correctly classified 981 out of 1,000 abnormal samples, true positive, with only 19 false negatives, false negative. At the same time, it correctly identified 984 normal samples, true negative, with only 16 false positives, false positive. Based on the data obtained, the following performance indicators can be calculated. The results presented in slide 7 demonstrate the high efficiency of the constructed classification model according to the main quality assessment metrics. In particular, the accuracy is 98.25%, which indicates the model's overall ability to correctly classify both safe and unsafe records. A recall of 98.1% indicates the model's ability to detect the vast majority of truly dangerous cases without significant losses. In general, the obtained metric values indicate the balanced and reliable operation of the model, which allows for the effective detection of threats with a minimum number of false positives and false negatives. For a more visual analysis of the effectiveness of the constructed LSTM autoencoder model, the distribution of the reconstruction error, MSE, and the dynamics of loss changes during training were visualized. Slide 8 shows the distribution of reconstruction error for normal, marked in blue, and abnormal, marked in orange, sequences. As can be seen from the histogram, the MSE values for safe, normal samples are concentrated in the range from 0 to 0.06, while the errors for abnormal samples are mainly in the range of 0.32 to 0.38. Such a clear gap between the two distributions indicates effective training of the autoencoder on normal behavior patterns and allows setting a threshold value for sample classification. The position of the 95th percentile on the training set of normal samples is between these groups, which ensures high sensitivity and specificity of the model in detecting anomalies. Slide 9 shows a graph of the change in the root mean square error on the training and validation samples over 50 training epochs. A rapid decrease in loss is observed during the first 10 epochs, after which the curve approaches a plateau, indicating model convergence. The absence of a significant difference between the train loss and validation loss curves indicates stable training without overfitting. The final loss values on both sets indicates a high level of the model's ability to reproduce the normal behavior of IoT nodes. The study implemented and experimentally investigated a model for detecting routing anomalies in IoT networks based on an LSTM autoencoder trained on normal data. The proposed model demonstrated high efficiency in detecting atypical behavior of network nodes, achieving a classification accuracy of 98.4%. The main advantage of this approach is the model's ability to detect anomalies without prior attack labeling, which is especially relevant for real IoT environments with limited resources. Thank you for your attention.